So folks, now that we've gone over and reviewed how to upload this CalcPlot 3D script in the previous video, and we've looked at this multivariate function that's looking at temperature data and wind velocity, and from that determining what we call the wind chill, let's go ahead and look at this graph represented in 3 dimensions from CalcPlot 3D. And we're going to, so that's what I'm asking you to do, number 8, is just to explore that graph. And then we also want to, from the graph, determine what w of negative 35, comma 50 should be. So just as a reminder, w of negative 35, comma 50 is asking the question, what is the wind chill when this independent variable is negative 35, that represents the temperature, and this represents the second independent variable represents the wind velocity. So let's take a look at that. So here we have the graph of this 3-dimensional surface that we're looking at. And I just want to point out that I've labeled the axes here just to help with the interpretation. The goal is to plot the wind chill, and we're thinking about the wind chill, that z variable, as a function of 2 other independent variables, the independent variable temperature, represented on the x-axis, and the independent variable of wind speed, represented on the y-axis. And remember, when I say they are both independent variables, it means that the temperature has nothing to do with the wind speed, per se. So one thing I want to point out, I graphed this, or I represented this data in such a way that you've got this clear mesh plane. That's the xy plane. Normally when you graph a function you won't do this, but I went ahead and graphed the xy plane in clear mesh just to remind you that those are where the domain values are coming from. They are these points in the xy plane. Each one of those points is assigned a coordinate, a real value, which is the third coordinate of our ordered in tuple. So for example, in one of your questions you were asked, what is the wind chill when the temperature is 30, the wind speed is 35, and the answer was that it's 14. Okay. So also we're asked to determine a particular coordinate. So I'm looking down on this so you can kind of see this like our table that we looked at before. So this should looking at the graph this way should kind of be reminiscent of that table. And in this problem that we're asked to look at, I am saying, okay, when the temperature is minus 35 and the wind chill is 50, what is the corresponding, the wind velocity is 50, what is the corresponding wind chill? And so you can almost think about this just like we did on the table. We go out to the x coordinate of 35, we look at where that intersects the y coordinate of 50, and although it's hard to tell here, that is the z coordinate of minus 81, and that should sort of fit with this image here where you see, yes, when we've got these 2 x and y coordinates, the z coordinate is about minus 81. So let's go ahead and fill that in here on our pre-work. So this was minus 81. And let's go ahead and continue. The next thing I want to talk about is the domain and range for this graph. So you can see from this graph that I've plotted this. We've got tick marks between x equals negative 50 and x equals 45, and y between 0 and 65. But you'll notice I didn't graph that. I actually perfectly matched this table when I created this. And so you'll see, yep, sure enough, if you click up here, we've got this format the axes, and that's where I'm stating what the axes should be. But if we want to see the domain and range of the domain of the function I plotted, go ahead and click on this graph, or this line right here, and we see, yeah, I restricted the domain to be x values between minus 45 and 40, and y values between 5 and 60. And you can see that in the graph of what was represented here. Our x values go between minus 45 and 40, and our y values between 5 and 60. So how could we represent? Looking back at our pre-work, one way we could say that is that the domain of this function was going from minus 45 to 40, and crossed with 5 to 60, and this is being mapped to the real number line. Okay. There's other ways we could have represented that domain. So for example, I could have also represented the domain, so this is just the domain here. I could also have represented the domain this way, as the set of coordinates x comma y such that negative 45 is less than or equal to x, which is less than or equal to 40, where I'm saying what those x values are. And careful folks, I used x and y, and that's normally what we'll use. But here we were specifically using t for the temperature values and v for the wind velocity. So this is between 5 and 60 for those v values. So that's another way we could represent the domain. And in terms of arrow notation, what we're doing is we're saying that we're mapping from this negative 45, 40, across 5 to 60 to the real number line. And if we want to talk about, for instance, how an individual point would be mapped, we're taking the ordered pair negative 35, comma 50, and we're pairing that with the output value negative 81. So again, folks, as we showed in that earlier video, that's understood to be the element in the domain, and that's understood to be the element in the range because we were given this arrow notation in describing our function w. So there's our w. Okay. So hopefully that clarifies some of this notation here that we're going to use for domain for our multivariate functions. And now I've got one more topic that I want to look at, and this is the important topic of contour plots. So earlier I asked you on the previous page, I said we want to talk about all of the TV ordered pairs that will output a wind chill of minus 40. And if you remember, back up here there were two ordered pairs, this ordered pair and this ordered pair on the table, that outputted a wind chill of minus 40. But the question asked, do we think that there will be others? And hopefully you said, yeah. I suspect that there are other inputs that would also output a wind chill of minus 40. To help us see that and to introduce this topic, we're going to look at something called a contour plot. So let's go ahead and jump back to our CalcPlot 3D picture. And what I'm going to do now, folks, is I'm going to go ahead and advance this a step forward. You can see it says I'm on step 1 here. I'll hit next. That will bring me to step 2. Okay, it shows we're on step 2. By the way, folks, if you ever move these or you don't like the way it looks or you accidentally change something, you can always just hit refresh and it refreshes the current step that you're on. So I want to explore these, what I'm calling what are called contour plots. And so first of all, without explaining what they are, let's go ahead and turn them on. So to turn them on this graph, what I'm going to do is I'm going to click somewhere on the graph of the function that I'm looking at, which in this case is this final check box here where I've inputted the function for the output z. And if you click this image here, this is your contour plot image. So let's click that. And this will enable me, once I hit create plot, to create a contour plot, which I'll explain in just a moment. But I need to go ahead and set it up here first. So what I'm going to do is I'm going to say, well, I think my z values, kind of the most negative z values I saw were maybe something like negative 85 for z. And I'm going to have those wind chill values step by 5 degrees. So I'm going to change that to a 5. And I think that's probably more than I need. I could probably get away with only about say 26 of these. I think that'll be enough. Okay. So now I'm going to go ahead and hit create plot. And at first this CalcPlot 3D just kind of gives you this bad image here. But as soon as I click it, what we see is our contour plot. So careful, folks, there's a few different images that we're looking at here. This is called the contour plot, whereas this is the level curves of the graph. Okay? So if you look at this contour plot, what we've done here is we've started sketching lines that or curves anyway, that correspond to various z outputs. So you can see here we said, okay, when we started building this, we said we wanted the contours to start at z equals negative 85, and then I spaced them by 5 apart. And we've got this nice image which shows you any XY ordered pair on this line, so if you look down on this, like on the XY coordinate system, then any XY ordered pair on one of these lines will output the line's stated Z value. And this is what we mean by a contour plot. These individual lines here on the contour plot are called contour lines. And if you look over here in 2 dimensions, we have this nice 2-dimensional representation of our graph. And here the contour lines, when they are projected onto the XY plane, are called our level curves. So one thing that's really nice about this CalcPlot 3D is I can click either on, well actually, I can click on this XY coordinate system over here. So hopefully you can see my mouse. I'm moving along the XY plane, but you see the corresponding point in 3 space. And when we talk about solving the equation, where is the output equal to -40, there's that corresponding contour line that we wanted. And any ordered pair, this is my domain space, right, x comma y, any ordered pair along this level curve here corresponds to an ordered pair that gives an output of -40, and that would place us on this contour line on our contour plot over here. So what I'd like you to do in this problem is I just want you to give a rough sketch of this contour plot. That's the 3-dimensional graph. So maybe you want to adjust this in such a way that it's kind of easy for you to look at. And you don't need to sketch, I mean, here we've got many, many different contour lines. You do not need to sketch them all. Sketch a few of those if you would, please. But make sure that you specifically include the contour when z is equal to -40. One other quick comment, folks, is that if you're looking for kind of a way to help understand these contour plots a little bit better, I think of this graph over here, this where we've got the level curves. This reminds me of a topographical map from hiking, and each one of the level curves on the topographical map corresponds to an elevation on that map. So if you've used topo maps, you know what I'm talking about. If you haven't used them before, don't worry about it. But the point is then I can use this 2-dimensional representation with these level curves to actually construct the 3D graph of this object. And you're going to want to learn how to practice going back and forth between these 2 scenarios. Okay, folks, that basically finishes us up. There's one more question here, and I'm going to leave you to answer that. I went ahead and answered everything in the last 2 minutes of this video for what goes where, and I'll let you decide what those are. So if you need to backtrack in the video, feel free to do that to try to figure out the answers to these. Otherwise, folks, that finishes up this pre-work. Go ahead and work my math lab for this, and I will see you in class. Thank you.